This is my first look at a QIC cartridge that somebody that found my YouTube videos and website has sent me just to evaluate. Here's the brand, Data Electronics Inc. Looks to be early 80s. And this is the model. Now, when I put this in and ran it, it seemed to be in pretty good shape. But by the time it got to the end of the tape, there was definitely symptoms of sticky shed syndrome, to the point where I think it was starting to slow down towards the end, and it definitely got caught up at the end on the reversal after it reached the end of tape hole, end of media holes there, and tried to reverse. So I will definitely be baking that tape again, or I should say baking that tape for myself for the first time for probably at least 4 days in order to make that work well. I will be using a procedure, of course, thank you very much, Windows. I'll be using a procedure like I show here on my website at QIC-24 under the tape baking section, and I'll just be using a process like this. I won't go into that right now. I'd rather go into this tape. It should have been written by a Tandberg, and this should be a picture of the model, or a very like model. The Tandberg data looks like a 3319 model. And what's unusual about these is that it uses a QIC-24 hardware interface. Now, I don't think that's going to make any difference on the magnetic signature on the tape, on the data block analysis that I do, and we'll get to that in a moment. I expect that to be the basic QIC-24 interface, and we're going to find that out very, very shortly here. So, but just so you can have an idea, this should be a representation of the tape drive that would have originally written this tape. Okay. So, I put it in my universal QIC reader, the exact same one that I demonstrate right here on my reader hardware page at QIC-24. And I just read logical track 0 in its default position. I didn't do any fine-tune track alignment adjustment or anything more advanced like that. And, you know, I don't know why, I guess it was lazy, I didn't even hook up the scope to look at what I saw live. So, we're going to see it for the first time right here. So, I have a data capture of this. Over here, I'm exporting this right now. So, I've opened it again in another window. And so, for the first time, live with you right now, my ever-growing YouTube audience, I am going to review this and see exactly what kind of format it is. So here it is. First thing I'm going to do is to use my scroll wheel and zoom out on the Saley Logic Analyzer. I'm using version 1.1.15 Saley Logic Analyzer. And I don't think I'll just start at the beginning, right here. And what I'm going to do is I'm going to find the noise section. This is the noise section. If you want to know more about the noise section, I think right here in exporting, I have a video about identifying noise. Hopefully that'll help. If you had questions about how I export, that's the case right here. So we're going to go through this. This is the noise right here. And I'm going to zoom out until it becomes incredibly obvious when it disappears. Just hit the right arrow here a few times until I see this. Oh, there we go. Okay, so the noise subsides, and now I see what I would expect to be a preamble. So let's zoom in real close and see what's on this transition edge. And sure enough, this is a preamble. And it looks like, if it's like other tapes I've seen, this gets narrower as time goes by. Let's see if it changes here as I scroll. Yep. There it is. See how it gets narrower? See how that changes? So what I imagine happening is the tape starts writing, and it's speeding up as it's writing. And so we actually see the compression of that of that very, very long, elongated, extra long preamble. And so now you notice these look much closer together than they did at the beginning. I won't even bother with the measurements there. But this is, again, what I would expect on a QIC-24 cartridge. So now that I've done this, and I've gotten to about this point, I'm going to zoom to just when the lines disappear, just a touch past that. Then I'm going to hit the right arrow, and I'm going to look for the first data block. And I expect it to be a while, because this QIC-24 preamble is very, very, very long. It can be up to 450,000 data pulses, 450,000 magnetic flux transitions for the first lead-in preamble before the data blocks begin. So it's no surprise that we just keep scrolling here and scrolling here before we see anything. Now, if it takes more than another couple seconds, I might get impatient and bump the scroll down here at the bottom. So I think I'm going to get impatient. Ah, wow. Okay, we pause this for a moment, and resuming exactly where we left off. I didn't touch anything here. All right, so this is where the data begins right here. And I'm not going to zoom in. I'm just, notice how the color changed, because the zoom that I'm at is just perfect. Ah, right there. There's that edge. There's that edge. So here should be the first data block. That's probably, I'm not sure how that looks. Let's find out. Now we can zoom in. First data block should be right here. And I can tell by that density change. All right. So this immediately looks like GCR45, as I would expect with QIC-24. I would expect the beginning of the data block marker to look exactly like this, followed by these three. So basically, this is 00111. That is the data block marker. And we know that if we go over to QICreader.com, let's go over to QIC-11 and QIC-24 format here. And that pops us over to this site, which is the first page I've ever done on this stuff last year. And let's see what I mean by data block marker. So, data block marker. Look, I have a whole section on it. GCR code 11111 00111. So that is the data block marker. And you can read more about that here in this section on the data block marker if you're interested in where that comes from. So, yep, right here. So this is the 00111. And if you're interested more in how GCR45 works, I have that section right here on this page. Again, to find that Universal QIC tape reader, click QIC-11 and QIC-20 format and follow the link. Okay, but anyway, here's the various tables for what all that means, etc., etc. I won't go into that right now, just so you know why I think what I think when I'm looking at this. Okay, so this looks good. This looks like a nice, strong data signal. I can almost tell you what it is. Just for fun, I think I will. I'm going to tell you what it is. It's repeating characters of 00101. So, and I guess what that would be the hexadecimal nibble. 00101 translates into a binary value. Oh, let's see here. I wrote my programs to do this, so I didn't have to. You know what? That can't be right. That's fascinating. Only reserved GCR45 nibble groups or GCR45 codes start with 00. The first one is the data block marker 00111. The second one, if I'm not mistaken, is Let's see if I'm right about it. Data block, control nibble, blah, 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 blah. File marks. Look at what a file mark looks like. 00101. So I can immediately tell that the very first block, all right, that's done exporting, I'll close that. The very first block of this is a file mark block. And I would expect the entire block of 512 to be exactly the same thing. So we start out on track 0 with a file mark, which is odd. That is a first for me. I have never seen the first block on the tape on track 0 be a file mark. Usually the file mark is at the end of the first file, and the first block is the first block of the first file. So this is news for me. Now, unless, did I miss something? Is this really the first block? Let's scroll back here a ways. Oh, no. That was not the first block. So I just didn't use a good method when I scrolled through here. Let's zoom down a little bit. I let an elongated preamble fool me. Alrighty. I'm going to zoom way out here. When all these lines disappear... okay. Maybe this is the first block? Let's see if this is the first block. Yeah, I think that's the first block. I just didn't go far enough. That was a really long preamble postamble in between there. I wonder if this Tandberg uses preamble postamble counts that are longer than what I'm used to. We shall soon see once deeper analysis commences. Okay. So this is the first data block. So here, just for fun, just to go through this exercise, I'm going to tell you what the first character is, what the first byte is, just by looking at it. So that's 11001. Of course, I realize this is very tedious. But hey, it's all part of the fun. 11001. Which one is it? It's a 0. 11001 is a 0. Now, of course, it takes 2 nibbles to make a byte. That was only the first nibble. I think I had a table over here, too, where one of these pictures, yeah, like this one. See, I had actually, and within my own pictures, I had embedded a direct translation from GCR-45 right to hex. And I sorted that first according to GCR-45 numerically. And then thank you very much, Windows. And then I sorted that again according to the hex digit. And this is just in my image here on this on my QIC-24 explanation page. Okay. So, I'll even tell you what the second byte is, just for fun. So the first one is 11001. The second one, is it a 0 or is it double 0? It's so hard to tell. Well, let's have lots of fun then, shall we? I mean, my programs do this, but I'm just doing some fun explorations here. Okay, so this is the beginning right here. 00111, that's the tape block marker, right? So 11001, that's the first nibble. But we need the second nibble to form the first byte. So, how can I tell if this is a single 0 or a double 0? Well, my programs do it really well, but I like to use this little trick right here where I copy 2 of these here in Notepad and see how well they line up. Yeah, there's only room for 1 in there, and as you can clearly see, there's room for 2 in there. But there's only room for 1 in there. So, measuring it visually in Notepad is much more tedious, but can be a little bit more fun than my program's doing it for you. And here, these two fit fairly well. So I can see right away that this is 01001. All right, so there's the second. There's the second one. 01001. Just like that. All right, so, and what is 01001? Well, we'll go over to the GCR45 table, and let's find it. 01. Huh. One 11001. I'm sorry, I was wrong about the first one. 11001 is a 4. And 01001, that's a 0. So, the first byte is 40. Look, it's an @ symbol. Great. Okay. All right. Well, I won't bore you with that anymore. I'll just look through here and let's look at the end of this data block. Now, if this is QIC-24, it's about 500, well, it's not about, it's exactly 512 bytes long, plus a data block address and a preamble postamble. Now, this looks to be about the right length of preamble postamble that I was expecting. Sometimes they get much longer if they're rewritten. And maybe they're much longer before and after a file mark. I haven't dug that deep yet. So some of this I'm really looking at for the first time. Yeah, this looks right. A bunch of repetitious characters followed by some ones that are clearly different. And somewhere in here would be the block address and the CRC. All right. So it looks like QIC-24. Pretty standard QIC-24. A few things threw me because I wasn't really careful there, like accidentally not finding the first block, but there you have it. So I'm going to zoom all the way out here, and we'll just look at this as a whole. The entire length of the tape was about 85 seconds, a little bit shorter than 85 seconds, and that's about exactly what I would expect from a DC 600 length or 600-foot tape. So let's have a look at the end now, just to see what that looks like. So here's the noise again on the end. And I'll scroll backwards now, until I find the last postamble on the track. All right, let's zoom out a little bit more, because it just isn't going fast enough. Get past the noise here. Come on, you can do it. Interesting. This is further back than I was expecting. All right, this is way further back than I was expecting, which indicates this track may not, the data may not extend this full track 0, which is fascinating. Okay, it ends right about there. Where is that? Interesting. Now, that's definitely a postamble, but that ends right there, and that's at 75 seconds in. That is a long space to be wasted at the end of that if the data isn't done writing. If the last block I see here is a file mark, then I would expect that to be the end of the file on this track. All right, so we zoom out to about that level, and yeah, right about there. And let's, oh, there it is. There's the last block. Okay. All right, well, just looking at this, I can instantly tell this is not a file mark. This is definitely real data. Definitely real data here. Okay. So, that being the case, I don't think it's bad that the last block ends 8 or 10 seconds before the tape ends. It's just, I'm not used to that. So I would fully expect, given that this is not a file mark, for the other blocks of this file to continue on the next track, on track 1. But we shall see here very, very shortly. Okay. Well, where should we go now? What should we explore now? Oh, I'm going to tell you why. I know what I wanted to do. I wanted to tell you why I can tell it instantly it's not a file mark, but it's real data. You see all these lines, they vary, right? You can definitely see varying distances there. A file mark would be a uniform, repetitive nibble throughout the entire block. And let's see if we can find it. Why follow-ups? Why can't I find things on my own page? Why? Really? Alright, well sorry. URL's case sensitive, excuse me. Hopefully I edit that out. If not, I apologize. File mark block. This is what it looks like. Here's the file mark block. So, that has the 00101 right there. And it's the same throughout. And I think I found that on one of the early blocks, which indicates that the first file is extremely short. But, okay. So, just based on visual inspection, I'm going to say this is true QIC-24. But, let's confirm it for sure, because QIC-11 and QIC-24 look extremely similar. The only difference is a few bytes right here at the end. And visually, I can't tell that. You know, maybe I could, if I did some calculations and measure the beginning to the end between the preamble and the postamble. I'm not going to go that far. Why? Because I have programs that answer this question for me, that I wrote. Oh, they're so much fun. Yes, they are so much fun. Okay, so now I am going to use these. So all you're going to do is watch me set up the run sequence for my programs here, and see what happens. Now, this program should take me about 2 to 3 hours to run all the way through. But let's see if I can get a glimpse of what's going on before it reaches that point. So, I have this source text file that I use to specify the file names that I want to work on. And my program is written in the very antiquated and highly underused, it's underused because it's very, very old, Lotus Notes. And so this is a Lotus Notes database that has Lotus script in it. I wrote all this stuff just because, well, this was my tool of choice because I just knew it the best. And instead of learning a better programming language for all this, I just wrote it all in something that I knew. So my apologies to those that might find it difficult to copy me, but hey, it's close to Visual Basic. Hopefully that's good. All right, so I'm just going to click this master run format here and run the program. Now, that's not what I want. Oh, well, I ran the wrong one. I don't even know my own programs, man. That's master run block repair. Oh. Well, I didn't even create a button for that. I just started creating all these buttons for stuff. Alright, you're going to watch me do this just because you can. Over here in Agents, I believe I wanted to run master run QIC-24 format. And there it is. I'm going to create a button for it, just so I don't have to go to this user interface. Okay. What I'm doing here is absolutely of no value to the QIC decoding process. You're just watching me in my user interface here with Lotus Notes. But if you find it interesting, cool. All right. Create an action. Simple actions. Add an action. I'm going to run an agent. And it's going to be master run QIC-24 format. There we go. Oh, do I want an icon? This antiquated version of Lotus Notes gives me these icons to choose from. Yeah, there's an icon. There we go. Alrighty. Now I have a button for it. Alright, this program takes about 3 hours to run. And it started working. Now, before I go into this, I'm just going to do a little review to help you understand what this program does, just at a very high level. So if you go back over here to QICreader.com and you click on Bytes Translating, this is the thing that I'm doing now, the Bytes Translating. There are these stages, and I have a different program for every single stage. And actually this is more than just the stages. This is like the whole thing. So stage 1, capture the magnetic flux transition data pulses to a logic data file. I've done that already. Stage 2, export it to a CSV file. I've done that already. If you click these, it redirects you to my pages that talk exactly about how I do that. Now, what I haven't built the specifics out yet is stage 3 through 7. I haven't demonstrated this yet, and I'm not quite ready to do that just because there's so much code in there. But right now, the program I just ran, which is what I just created this button for here, this master run QIC-24 format, that runs stages 3, 4, 5, 6, and, well, I guess it just runs stages 3, 4, 5, and 6. And then stage 7 is something that I do manually, which is all kinds of fun. So, program I just ran does stages 3, 4, 5, and 6. And I split it up into 4 stages because it was so complex that I had to create 4 separate individual programs for it. And that's one of the reasons it takes so long. Now, because I did... Yes, okay. Thank you. Thank you. Windows keeps bugging me. It doesn't like my color scheme. So that's fine. So what we're going to look at right now, since we really can't watch the program run, that's not all that meaningful, we're going to look at the results of the program as they appear. And here they are, right here. So right now, stage 3 is running. It's running the decoding to data block strings program. And so here's the data block strings right here. Master decode log is what I like to use. Here's fun. This one is a bit too long, and the first one is always the longest because this basically is a log of ruling out all of the noise. Oh, what the heck, let's open it. We're going through the process, right? That's why you're watching this. Let's open it. Alrighty. So here it is. This is basically every line on the CSV export, and my program adds stuff to it. So the CSV export is really just this time frame right here. I've added to it. So the log tells me exactly what translation it is for the timing distance between pulses. So in this case, it's basically the distance between, these first two pulses here. Now, there's a lot of pulses, right? There, that. I think here's the first one. I think it was 0 to this. The second one is this. Now, see, this is a noise, so this is not real data, but it doesn't know that. My program actually looks at every single data pulse, every single pulse on this logic analyzer. It's the only way it knows anything. And so, here in this decode log, this is the noise. It basically says, well, this spacing could have been a 100, but this next one, it's an X. It's too long. It's not valid. Right? This one could have been a 100, this one could have been a 10, this one could have been a 1. But the rest of these just don't exist. Well, the program looks for a long string of these, which would be the preamble. Right? A long sequence of valid ones. And, oh, this is interesting. It finds it. First it finds these 10s. I'll bet before this it finds some 100s too. Let's see. Remember when I said that when the tape was originally written, it looked like it started to write while the preamble, it ramped up to speed. That's why the spacing at the beginning of the preamble is wider than the spacing at the end of the preamble. Well, here it is. The first couple of them it identified as 100, which is a wide valid gap. Medium valid gap is a 10, and it just thought that these were 10s for quite some time, until it got down to these 1s. Now my program counts the 1s now. It counts sequential 1s. As soon as the 1 changes to a longer gap, which is a 10 or a 100, then it drops out. It basically says you're no longer a preamble. And actually this is a case where it happened here. And at the beginning, that's very normal. The point is, the program is just looking for, it's counting how many 1s are here. So, if it gets to more than, how does my program do this? I think if it's like less than 80, it's not a preamble. As soon as it gets to 80, it says, hey, it's a preamble. It's a short preamble. And my program, because I wrote it to do so, will actually classify how long the preamble is. After it gets to another length, it goes to preamble normal. You know what? I'm going to tell you exactly what that length is. I didn't mean to go this deep, but I'm just doing it. Just because I think you might be interested in it. So let me go to this program here and tell you what I have. Okay, preamble. Here's my code, the Lotus script, lovely Lotus script. Here it is. Okay, I guess if it's less than 50, then it's not a preamble. If it's greater than 50, it's a short preamble. If it's greater than 120, it's a normal preamble. If it's greater than 3,500 pulses, it is an elongated preamble. Greater than 15,000, it's long. Greater than 30,000, it's long 30K plus. Greater than 450,000 is long 450,000 plus. Now, the reason I came up with those was because when I was reading in the documentation about the preamble, as we see on this page here again, oh gosh, where do I have the preamble? Preamble. Some of these sections, it actually specifies this. According to the bottom of page 13 of the CYPR manual, it gives these specifications. So a few of these manuals that I used to do research on this actually made these classifications. It said normal was 120 to 300 flux transitions, and elongated was 3,500 to 7,000 flux transitions, and along was 15,000 to 30,000. So you see how I made those distinctions. I guess I skipped the 7,000 mark. I just went right from 3,500 to 15,000. Question is, what's between 7,000 and 15,000? It's too long to be elongated, but too short to be long. All right. Anyway, I don't want to go too deep into this. This is just some of the stuff that I did to develop this. The point is, this is the log that decodes all this. So you see how we go from normal to elongated, now to long 30K, and that goes on for a while. Long 30K, and doesn't look like it gets much further than that. Nope. Here we go. This is the first data block right here. So, after 280,924 sequential preamble data pulses, which is, longer than 30K but less than 450K, it comes up with this. Now, my programs, every time it drops out of the postamble, does a calculation. And it does a calculation on the timing. And basically what it does is it takes an average of all of those to say, I want to know what the average one is. And then it uses that value throughout the rest of the data block. It does that over and over again for every single preamble, postamble. It greatly increased the accuracy of these programs on some of these older tapes, or tapes that might have varied in speed when they ran, because it just wasn't being so specific about the timing. It wasn't set. Whereas if it varied too much at the end of the tape, it started to error out. It kind of tracked along with it. So, if you will, it's my program's version of setting the phased lock loop that is used throughout the rest of the data block. But that phased lock loop then is reset for every single preamble, postamble between data blocks. So, here's what we have here. And it identifies that the average preamble pulse time is 1.104 microseconds. 1.104 times 10 to the negative 6. That's the scientific notation there. And here's the calculation that was used to get that. It's this value, which is basically a huge 0.310 seconds, and that is a very, very long time, because this is a very long preamble. That's a very, very long time, divided by the number of pulses in there, which is 280,924. And it comes up with this now very accurate number. And then I multiply that times 5, and I come up with a nibble duration, which should be the exact width of a nibble. 5.5216 microseconds. Now, my programs don't use that just yet, but in the future they will. So we'll leave that right there. All right, it identifies that in the sequence of my program, this is the first block it's found. So it identifies this as sequential block number 1. And here, my programs are reporting to me in this log that it's setting the lowest threshold value as, I believe this is 0.55 microseconds times 10 to the negative 7th. And the 1 threshold is 1.656 microseconds. The 1-0 threshold is 2.768 microseconds. And the 1-0-0 threshold is 4.086 microseconds. So this is the timing that my program has set by this, based on the parameters that I have coded into my program. And I believe I just use multiples for that. If we go here to preamble timer, low multiple, 1 multiple, 2 multiple, 3 multiple. Oh, I think I set those right here. Yep. The 1 multiple is 1.5. This is the upper limit, by the way. This is the limit where it stops being a 1 and then can become a 1, 0. So this is the upper limit. The upper limit is a multiple of 1.5. The upper limit of 1, 0 is a multiple of 2.5, and the upper limit of 1, 0, 0 is a multiple of 3.7. Anything longer than that is too long. It's an error. Oh, and a low multiple, meaning anything smaller than this, is just not valid either. So, this is what I use. And if I want to, I can change these slightly if I think it's going to get me better success. But this is really what I've worked with. Just kind of splitting it down the middle like this. It's just really, really increased the accuracy a great deal. So let's see here. We're in this log, and we've seen all this magical stuff. My program did all this stuff to identify what it needs to in order to now identify the subsequent data pulses. Okay, so the first characters it finds is 10111, which is exactly what it should find. That's the data block marker itself, which is good. The next thing it finds is 11001. Now, notice the nibble, which is 5 spaces, so to speak. I'm going to call them spaces as if it's the space on a, in text. I think I'm going to draw that out here. I think that actually is helpful. You see how I just typed that out, and instead of putting zeros in, I put spaces. Well, in a monospace font, like there is in Notepad here, that's very, very specific. And so what I just did here, very much resembles what you see here. I'm just going to zoom in on a random space here. Oh, that was too far. Very much resembles what you see here. 11001, right? So, but the way I did it, this is one space. I'm just going to start right here. 1 space 1 space 1 space 1. Now that one looks a little bit wider. So maybe I'm visually off here. Maybe this is only 1 space and this is 2 spaces. Yeah, and I think it is, actually. But you see what I've done here is just, sorry about that, I'll close this one, is just use these spaces. So in this case, 1 space 1 space 1 space 1. So it just counts the distance, the spaces. I don't know if that made any sense. Hopefully it didn't confuse anyone, but hopefully it was helpful. All right. So now that that's the case, we can see here that the nibble 11001 falls right in between this. So this can become a little bit tricky to translate, which is why I have 2 separate programs to do this. I have one program to dump this as an output, and then another program that reads that output as an input, and then turns that into nibbles of 5 GCR sets of, ones or zeros, and then translates those directly into hexadecimal characters. And I am using ASCII characters as hexadecimal representation and working with that all the way up until the point where I paste it into the hex editor. Okay, but anyway, this is what we're seeing here. Oh, and by the way, I wrote something in my program that gives me a centering. And so far, immediately, we're seeing very, very good centering. What that means is, how close to the center is this data pulse? Well, this one is, right about in the middle. 50% is perfect. So these are all hovering around this. And if anything is below 20% or above 80%, I have a little warning flag. Like right here. This is interesting. How the heck did that happen? My calculation off? I think it might be. I think my program might have a well, let's call it a glitch, will you? Because I know this is right. And 3.208 is certainly lower than, no. It's wrong. I have been lying to you. You see how confusing this is? I have been lying to you for the past 8-10 minutes. Because this should be 10111. Excuse me. This should be 100111. Not 10111. Somebody should have yelled at me halfway through the video there. I didn't hear you. Okay, sorry about that. I'm really sorry about that. In my own documentation that I referred to but didn't read, look at that. 00111. It's very, very easy to confuse this. So I'm sorry that while explaining this to you, I'm dropping the ball here. 00111. So my program's got a problem here that I just found. And it's going to miss this block. What the heck happened here? I mean, the centering correctly identifies the fact that it is over tolerance by 140%. As a matter of fact, that's relatively well within the next zone. But why it identified it as a 10 instead of a 100, I do not know. I wonder if it's because these things are set after this computation is done, but before this is printed. See, now as I'm trying to explain this to you, I might be finding errors and glitches in my own programs. I'm not sure if you should be happy about that or sad. Or neither. But anyway, glad I found that and glad you all witnessed it. This should be 10111. That's what it should be. And so my programs are going to say there's something here, but it's not a valid data block because this doesn't start with 100. Now, let's fast forward here. See if I have the same problem with the next one. And how am I going to do that? I am going to... What was I just looking for? There we go. That's what I was looking for. Sequential block 1 nope, that's not it either. It resets. My program will reset this if it identifies that a preamble has started again. So, hang on here. See if we can find these. There it is. This is the first block. Now, in this case, my program would have erred. It would have identified this as block 1, when I can clearly see just by looking at my own logs that this is block 1. So as you're watching me explain my wonderful programs to you, I'm finding problems. And I think it's a calculation problem where I don't do that recentering soon enough. This one's just fine. This one's exactly the way it should be. 100111. That's what it should be. And what it's counting is right here, 1, 0, 0, 1, 1, 1. That's what you're seeing right there. The nibble, of course, doesn't start until the double zero. But we should be seeing 1, 0, 0, 1, 1, 1 here. And we do. So that's very curious. I'm going to have to look at my program and figure out why it did that one thing wrong. So, you all got to witness this. And I've used this program on a lot of tapes. Successfully, I might add. So this is cool that I find this while recording this video. Alright, anyway, here's block 2 now that I think it's doing better with. And all the centering there looks very, very good. The data read on these first few blocks looks very clean, just so far. Ooh, here we have an elongated preamble. And I'll bet this is the file mark. I'll bet this is the file mark. I'll bet it is. I'm going to have a little fun here. And I'm going to run, I'm going to interrupt this process and run another program on top of it. This, like I said, this program will take a long, long time. Right now, just in the period of time that I've been talking about this, it has identified 3,400 blocks right now. 3,400 blocks. I expect there to be 10 to 13,000 on this track. So, we'll see. And I already know that it missed the first one. So I'm going to have to go find that. So just for fun, just to complete this video, I am going to run another program on top of this one. And it's going to be running this out of sequence, but it shouldn't hurt it too bad, because I'll stop it before it bumps into the next process. Alright, so now I'm going to check my own work here again, because now I'm questioning myself. I'm going to go to the bytes translating section, and I'm going to say, what program am I supposed to run? Decode data block strings to hex. Yes, that is the next program I should run. So I'm going to run that over here while the first one is working on the data that the first program has already identified. So let's see what that looks like here. That's the program I want to run. Alright, let's see what we got here. Here it is, it's running. Oh, identified bad block number 20. Alright, so far so good. Data block strings. This process goes much faster. We're at about 400 blocks. Alright, so I'm jumping ahead here a little bit. Well, the next thing I want to do is I actually want to show the data block strings. Now, sorry that I'm jumping around, but hopefully it'll go through my process. Hopefully the process will make sense. Now, I mentioned that this master decode log here that we've been looking at is the first stage. And there's two outputs of this program. The master decode log, which shows all this very verbose information on every single data pulse. And then there is a data block strings output. And so if we were to look at the first block, data block strings, the first block, which is right here. No! Here it is. Data block strings. This is what we see. Now this might make more sense to you because it's a bunch of zeros and ones. Now all it is right here, this section right here. Whoops. Let's scroll up. This section right here is the first data block. Now, I know it's really the second because you all watched me find the mistake I made, or maybe it wasn't a mistake, it's the error in the program because it failed to catch the first block due to a timing issue. An invalid timing issue, I might add. But here are the zeros and ones. So another program goes through and reads this file, and it looks at it line by line. By the way, this is one line. Notepad makes it look like multiple lines because it's Notepad, and it after 1028 characters, it wraps. So really, it's 1028 times. No, it's not 1028, excuse me. 1024 characters. That's 512 times 2, 1024. 1, 2, 3, 4, 5 point something. Like 1024 times 5.3. That's how long this is. All right. The point is, these are all of the GCR4, 5 zeros and ones in this data block. And that includes the data block marker, which is right here. All of the nibbles of the data block, and then all of the nibbles for the block address and the CRC. And then at the end here, we see all these ones. There's the postamble. Okay. So another program goes through and reads this and dumps it into a more meaningful format. And so that other program I already started to run a little bit early, just so you could see what this looks like. And, oh, look, we're finding some bad blocks. All right. This is the point at which I'm going to confirm with a high degree of accuracy whether or not this is QIC-24 format. All right, where do I want to go to see this? I want to go to data block strings. So if we go to data block strings, that's the output of the second program. So I want to go to data block strings for the first block, which I think is going to be up here. It's like working with a moving target. And there it is right there. Okay. No, I just looked at that. I'm wrong. Let's look at the data block byte strings conversion log. This is an interesting one. This wasn't very useful to me. It was kind of an intermediate step. This just kind of wastes space to a certain extent, but it's at least telling me what nibble was identified here. So for the first block, which is really the second block, it identifies 090100000000. All these zeros, all the way to nibble 1024, right here. Nibble 1025 and 1026 should be the track number, which ironically should be 0. Nibble 1027 should be the... Oh, maybe it's not as bad as I thought. Should be the block number for QIC-24, which, surprise, surprise, is 1, not 2. What am I looking at here? 1 should be here. That's 100001. What is that? And by the way, that wasn't binary. That was hexadecimal. You know, since I started using these, I've never dug in this closely to see what's in here. Let's look at a quick hexadecimal. No, I don't want to do this. I don't want to do this. I don't want to do this. I just want you to give me a Google search, okay? Can you give me a Google search? Thank you. Or Bing. Fine. Bing will work for now. Hexadecimal. Hexadecimal converter right here. That can't be right. Okay. Unless. Hang on now. I could be confusing myself, but if I'm confusing myself while you're watching me, what does that mean? Track 1? It's track 1. Alright, so I lied to you. Nibble 1024 is not it. It's actually nibble 1025. Because it's a pair. It's a pair that starts at nibble 1024. That's the end of the data block. So the end of the data block is 00. The track number here is 01. This is interesting. So for the first time I'm learning that the default track 0 on this thing is actually track 1. Fascinating. Excuse me. Let's see if we can confirm this. And then this is block number 1, which might mean that the block number 1 was rewritten due to error. And the CRC is DF8B. And then here we have the post-amble. So this is an intermediate step. This program I wrote here is an intermediate step between programs that basically determines how it translates from GCR45, this code, this GCR45 code, right to the hexadecimal character. And it is a hexadecimal character because that's what I'm eventually going to paste right in here into HXD to create the binary file. So, sure enough, DF8B. So that's the what do I want to say? That's the CRC right there of this block, DF8B. Okay. So now you've seen, with a little bit of jumping around, how we got to the master decode log, and then how we got from the master decode log to the GCR45 zeros and ones, and then a little bit how we got from from groups of GCR45 code to the hexadecimal nibble, or the hexadecimal value of the nibble, I should say. And by the way, P, of course, isn't a valid hexadecimal character. If I were to put a P in here, it doesn't do anything. If I were to paste a P in, it would object, because it says, that's not valid. That's right. Well, P stands for postamble and preamble. All right, so now you've seen, here's the stage. You've seen me go from this to this, to this. Here's the 3 stages. 1, 2, 3. So we've gone from this stage to this stage to this stage. Now there's another stage yet that actually just concatenates all of these things into a file, and I'm wondering, because it's been a long enough time since I've written those, where it is in here. Let's look at the data block bytes report. It should be in there. All right, here we go. Here's our first look. Here is our first look at what we see here. And so this is the first data block bytes report that is written by my second program here. It's written by stage 2. Or in this case, sorry, stage 4. Sorry about that. Maybe if I do this again, I'll get it a little bit more cohesive. Okay. Yeah, you know, maybe I'm not so crazy. My program came up with the same thing I did. DF8B. Look at that. Look at that. Okay. Well, I can tell you right now that the first data block, I think, was written twice. No, it's not track 1. It's track 0. And I think there was a nibble-wise shift. Not a bitwise shift, but a nibble-wise shift in this data block. Because that's clearly a problem. And I think my subsequent programs, which they'll read this file, would have found that. But here's our first look at the data blocks. So we have a data block here, and followed by a file mark. See these M's? That's the file mark nibble. That special one. And this is good. Now I can tell by this number right here, which is probably correct, that this really is the first data block. And the first data block was probably written twice, which means my first one that actually errored out, ironically, is inconsequential to this process. I still want to fix my program so it shows up on my report. But as it turns out, it was inconsequential to this process. All right. Now, at this point, I'm looking at this data block bytes report, and I confirm I am 100% certain we're dealing with QIC-24 here. So I'm sorry that it took me an hour and 8 minutes to get to this point. Hopefully watching it was of some value, at least a little bit of entertainment. Or you skipped ahead or something. But it is definitely QIC-24. Definitely QIC-24. So that's what we have here. Now, there's some minute errors that I need to work on here. Evidently, I found something in my program that could make this more accurate. But this is going to end up being a data block error. For one, I can tell you that the CRC isn't going to line up. You might notice that the CRC isn't checked yet. If you watched any of my other videos on CRC checking, that is a whole other program yet that reads this file and then does CRC checking on all of these. That program is right here. Stage 5, run the CRC calculator program. Stage 6 is run the data block counter program, which does a final check across the whole thing to see if there's any blocks in sequence that are missing, and then identifies those as problems. Anyway, let's see what we have here. You know what I can do just for fun? I'm gonna, while you're watching, just because you're here, if you've hung in this long, maybe you can hang out a little bit longer. I'm actually gonna run the CRC on this one, just for fun. It's gonna run on a subset because the first program is actually still running. Let's see what we got here. What stage are we at? Oh no. Interesting. Oh, it caught up with me. I think. Yep, it caught up with me because this is free. That means that it's done working. Well, I timed that well enough, I suppose. Alright, now I'm just deliberating. Do I want to run that or not? The CRC. Because I think that the data block bytes report has reset now to 0. And that if I try to reopen it, nothing's going to be there. So it might not work quite that well. Let's see if I can find this. So there's a lot of text files this dumps. And with one track of a QIC-24 format tape, my programs just waste a ton of space. I mean, a ton of space. You know, for example, here's a tape. There we go. How much did this thing use up? Only 6 gigabytes of text files. How about this one? Yeah, 6 gigabytes worth of text files on every track read that I do. That's okay. 6 gigabytes is nothing nowadays, so that's not a big deal. The value of what's happening here, I think, is much more important to the process because for the first time it enables us to read previously ununderstood and unreadable data because it was a mystery. Nobody knew what this stuff was. Not nobody, of course, but nobody that's put it together and stuck it on YouTube that I've seen so far and made a website like this about it. Anyway, sorry I'm rambling on about this. I'm just, glad you're watching this. Well, so I'm looking through here right now. I know what I wanted to do. I sidetracked myself. That happens. That happens with me. I wanted to see if the data block bytes report had reset itself. Well, it's the same size. Stopped at block 4500. $45.62. I will run it. Let's see if it happens. Let's see if I blow up my own program. All right. Where's my CRC checker? Where is it? CRC checker single file. No, that isn't it. There it is. CRC calculator, QIC-11 and QIC-24 format. I'm going to run this. See what I blow up with it. All right. So while it's writing that out, I should be able to look at it while it's writing it. So here we go. And I can. What? Oh my gosh, that's hilarious. The CRC was a match there? Alright, this is a mystery. Great when the first block is a mystery. Here we go. This one's right. It's a file mark, and the CRC checks out. By the way, what's the binary value of an M? Our programs say that, actually, over here. Let's see, what is it? The GCR nibble 00101 shall be converted to the data nibble 1111 to form the data field for the CRC generation and checking. There, right here, is how we figured out what the value is. So that's how you're able to calculate the CRC on an otherwise completely invalid nibble. It has a translation, a representation in real form, right there. All right, so let's look at some other of these things then. CRC verified. Here's the data block here. Here's the data block here. You know, these CRCs are looking pretty good. I think the first data block error was block 20. And there it is right there. So the first error I got on this whole process is 20. I'm still not convinced data block 1 is really right, but, you know, it might have slipped through somehow. 17, 18, 19, 20, 21. This QIC-24 is really great because the block sequence number in the entire tape is tracked. So if a block is misread or missing, I'll know that by finding a gap in the sequence. And so, you know, here I can compare two things. The data block number is written in the data block and the data block sequence count as my program finds the blocks in the sequence. Those are two different numbers. And it makes perfect sense that they're out of sync. How far out of sync is tracked by another program, which helps identify missing blocks. See, here's an example where the file mark block is written twice, and the block sequence number is identical. That's actually a QIC-24 error correction thing, where if the block is written once and it's an error on the readback, which is done read while write, then it rewrites the block. And so how does it know that, you know, that the block the previous erroneous block can be ignored? Well, a block with the same sequence number shows up in the future, and that replaces the old one. That's the logic behind that. And so I wrote my programs to emulate to do the exact same thing. And by the way, the data blocks counter, stage 6, data blocks counter program is exactly what does that. It's exactly what does that. I wonder how this is working on right now. It's still chunking away. Okay. So anyway, we're looking at the data blocks on the tape. A few errors. And we should be able to read those. But, just as I scroll through here, this is some interesting things. There's data here. There's real data here. Because I look at all these lines, these are not all the same. These are not just repetitious characters. There's some repetitious characters, but there's stuff here. And so there's real data, there's real programs. This is real binary. It's real QIC-24 binary. So, as this process goes through, we're going to see exactly what's on this tape. Once all these programs finish, then we're going to end up with basically one big file of the entire track that I'm going to be able to then look at in the HXD hex editor and make a little bit more sense out of, to do things like repairing of bad blocks and such. And that's what we're going to see. So, hopefully this was helpful. If you watched the entire hour and 20 minutes, I apologize. that it took me so long to explain all of this. I think if I try to explain it again, it might become a little bit easier. And I hope that it does. But this is a really good overview of my first look at one of these tapes written by this Tandberg model. What was it? The Tandberg 3319. That's where we started. So all of that, again, is what was on this tape. So thank you for watching. I hope you found this helpful, and I would love to hear your feedback. And let's say that this is a to be continued, because I really do want to explain the other segments of this program in greater detail. Thanks again. Bye-bye.